Hello and welcome to the AutoPIPE Vessel webinar. In today's webinar, I would talk about designing various types of shell and tube heat exchangers with particular emphasis on tube bundle and tube sheet design. First, we would see a brief introduction on AutoPIPE Vessel and mention some of the advantages of using the product specifically for tube bundle and tube sheet design, followed by several videos. The first video would cover a basic U-tube heat exchanger design and modeling and how to export drawing to various CAD softwares. Then there would be a video on fixed tube sheet heat exchanger. Following which, we would see a video on floating head exchanger and tube sheet design and how to modify some critical tube sheet design parameters. And finally, we would wrap up the webinar with a review of the Supplementary Design Data tab for tube sheet design and also talk a little bit about some international design codes. AutoPIPE Vessel powered by Microprotol is a very powerful software that can design virtually any type of pressure vessel, air cooler, heat exchanger, and tanks to most of the major global design codes like ASME, European, and British. One of the strengths is the ability to import thermal design data from HTRI, Aspen, ProSim, and Honeywell, as well as exporting to the major CAD software and plan design softwares like PDS and AutoCAD, SolidWorks, MicroStation. The software is ideal for both EPC companies as well as equipment design and fabrication companies. There are several advantages of the software, including maximizing productivity of skilled engineering resources, supporting a global market, and improved collaboration across distributed project teams. AutoPIPE Vessel offers a wide range of global vessel codes, including regional wind and seismic, including last 10 years of all design codes from French, American, British, German, Russian, and European. It also supports local analysis methods and comprehensive regional seismic and wind loadings for Canada, India, AC, European, Russian, GOST, British, Brazilian, and Spanish. There are several users of this product worldwide, including major EPCs like Jacobs, Technip, and Saipem, nuclear EPCs like Areva and Babcock & Wilcox, inspection authorities like Lloyds, SGS, and Buena Veritas, as well as oil and gas companies like Petrobras and ExxonMobil. Here are a few examples of some of the equipment designed using AutoPIPE Vessel from top left: a reactor vessel with many nozzles in close proximity, a distillation column with platforms and stairs, air cooler with all structural elements, and a vertical jacketed vessel on skirt. Almost every TEMA type shell and tube heat exchanger mechanical design can be performed, including some examples shown here, like a stacked heat exchanger, multipass exchanger, kettle type reboiler, and U-tube exchanger. AutoPIPE Vessel has powerful CAD export features, generating 2D drawings and 3D models for MicroStation, AutoCAD, and SolidWorks. Shown are some examples of 3D SolidWorks model created automatically from a designed exchanger using the interface feature. Some more internal details from SolidWorks models. Notice the detailed machined baffles shown on the bottom right. The SolidWorks tube bundle assembly in the heat exchanger shown above are assembled with proper mate features and hence can add tremendous value for checking interference and creating bundle assembly procedures. There are several advantages of using AutoPIPE Vessel for designing exchangers with complex tube bundle and tube sheet details, which would be evident soon from the videos that we would be presented shortly. Some of the key advantages are as follows. First, it supports design for all TEMA type exchangers. The entire tube bundle design can be performed via a single window, which makes data input fast and easy. Same applies for tube sheet design as well. The user-friendly dashboard enables design of complex tube bundle layout with minimal effort. The tube bundle layout is automatically generated. You can design exchangers and tube sheets based on various international codes and not just ASME. Complex tube sheet geometry and design case input are permitted. And last but not least, the powerful CAD export feature enables automatic creation of detailed drawings and 3D models. Now let's watch a quick demo for a U-tube exchanger design. First, we select the type of CAD software that we want to export the CAD drawings to, which includes MicroStation, AutoCAD, SolidWorks, all the way up till SolidWorks 2015. We choose the input SI units in this case, and also the drawing formats, etc., the unit system for the drawings. So we will design a shell and tube heat exchanger. As you can see, almost all the TEMA type exchangers are available. This shows some of the templates. This is shell type E, shell type F, split flow, double split flow, divided flow, kettle type, and the various different rear end types, including U-tube exchangers, fixed tube sheet, floating head. So we will create a simple BEU type exchanger. So we select the configuration BEU, and that opens the shell and tube heat exchanger properties window. The design parameters, you can see the design codes, various design codes like EN, CODAP, ASME, AD 2000 mark letter codes, GOST, these are all available. And also the local load methods include PD 5500, WRC 107. These are supplementary design features, the external pressure with or without stiffener, etc. The design conditions is the most important tab, perhaps. You enter the shell side and the tube side, temperature, pressure. You will design it for 0.75 megapascal, 250 C shell side, and 0.25 megapascal, 120 C tube side. We enter all the parameters here, the design conditions. The radiographic full spot, none, weld types 1 and 2. The load conditions are lifted, erected, operating, shutdown, test, blast, as well as you can enter up to five load cases. You can design for wind as well as seismic. Wind and earthquake. Shows all the different earthquake codes available. There's also another option for motion, the accelerations due to motion, which you can enter. The load combinations are automatically generated. Next is the operating conditions tab, and this is the geometry tab. Different types of heads. We will set 2:1 axis ratio, 6-inch weld neck nozzles, nominal diameter. We choose gasket and the shell inlet outlet configurations. The bundle, as you see, is the BU type exchanger that we are designing. TEMA class RCBNL, 30-degree triangular, square, rotated. We will keep triangular. We'll enter the pitch 25 mm, diameter 19. Straight tube length 6 meter. We can specify the tube thickness based on the gauge, BWG gauge, or we can actually enter the thickness. Minimum wall thickness, average wall thickness. So you can check from the reference help menu what these BWG gauge thicknesses are. We will enter 14, gauge 14. You can specify different thicknesses for first two rows. You can set tolerances and corrosion allowances. Bending radius you can set. The default is about 1.5 D. Okay, for the first two rows. The baffles, different types, disc and donut, segmental, double segmental, triple segmental, vertical with 30% cut. This shows all the baffle configurations that are available. Very nice pictorially mentioned. It's easy to refer. We will provide baffle either spacing or quantity. We can do it spacing. We will put 300 mm spacing. The gap option is there, OTL to shell ID. So TEMA recommends certain gap, OTL to shell ID, depending on the dimensions of the exchanger. So those are the defaults. You can change those. Tube sheet layout. Here you set the tube sheet layout design parameters, the tube bundle design. So it's a 2-pass exchanger. Let's say we put tube number 600. We will include sealing strips. You can also mention the shell ID. In that case, the number of tubes will be automatically calculated. But here we are referring to the number of tubes. So we are designing as per the number of tubes. You can include impingement baffles. We will include them here. We will include sliding rails, and you can cross tubes 1 by 1 or 1 by 2 using dummy tubes. But we are not going to cross tubes this time. So let's compute. So the program automatically calculates, and as you see here, the bundle report is generated, number of tubes maintained, and the OTL, the shell ID, these are all obtained and reported. So number of tubes 600, number of tie rods, sealing strips, sealing rods, minimum shell outlet free height for the 2 passes. Then the next tab is the reports tab, which details all the different contents for which you want to type the reports, print out the reports. Then the materials for the shell side. You can individually set the material for each head, shell, etc. So as you see here, the library is available, but we will be applying a default data option, which you can change from your default data library. So what that does is it populates the material with the default carbon steel material that you have set in your library. You can change that. So that designs the preliminary exchanger. As you see here, the top view is the 2D sketcher, and the bottom one shows a 3D model. You can right click and have different options. For instance, I have clicked on transparent shell. That enables you to peep into your tube bundle assembly. You can go back to your tube sheet layout, tube bundle layout, and make a couple of changes here. For instance, we are doing right click on the sliding rail and we're removing it. You can change similarly the ceiling strip locations. You can undo. One of the easier ways to change locations, etc., is to double click, and then that can allow you to enter the data, for instance default width, thickness, as well as the coordinate locations for the component. For instance, here we will be changing the location of the ceiling strip by changing the coordinate system, X and Y coordinate systems. So that gives you accurate control on positioning of your components in the tube bundle layout. We can change some of the tubes to tie rods by the option that is available, change tubes to tie rods. We will perform similar operation for a few other tubes. As you can see here, the software has already removed the corresponding end of the U tube from the other side. So we change some of the tubes to tie rods. It's very easily done by click of a button. Now if you want to change the tie rod back to tube, that option is available too. Observe the lower tie rod is changed back to tubes. Now we can change the ceiling rod dimensions similarly by double clicking and then adding, modifying the diameter, etc. You can erase tubes along a segment or along a line. So for instance, if I want to erase the tubes along this line, I can do very easily by clicking on that option. You can undo it very easily. You can erase tubes within a rectangle. Hold your button and then release it where you want to end the other vertex, opposite vertex of the rectangle. You can cross tubes. Okay, so that's very easy to modify the tube bundle assembly. You can also look at the longitudinal view. This shows the support plate, the baffles, which are numbered. So that gives us a very quick idea of how to model a simple BEU type, which is a U-tube type heat exchanger. Let's watch a short demo video of SolidWorks 3D model generation. The entire 3D model that you would see was automatically created in an AutoPIPE Vessel from the exchanger design file. Just like we did for the previous model, we will first set the CAD preference. Using the file preference option, you will select SolidWorks, and then we will complete the design of the exchanger and then generate the drawing, which in this case would be SolidWorks 3D model. As you see, the components are being generated parametrically. The complete 3D model is now completed. You see the top section view, floating head tube sheet assembly. You can see the amount of details, even the gasket details are shown here. This is the assembled body flange, studs, nuts. The front section view. This is the gasket details. The channel side pass partition plate. The ceiling strip, sliding rails, tubes, everything is shown. The body flange. This is the saddle. Now observe the details, like even the fillet radius is shown very clearly. And all these are automatically done. Channel cover with pass partition plate groove. This is the drill tube sheet, complete 3D model. This is the baffle details, assembly. This is the shell, this ellipsoidal head. Now another very common type of heat exchanger is the double fixed tube sheet heat exchangers. So let's now watch an AEL type exchanger that can be designed using this program. So just as we did in the previous video, we'll choose shell and tube heat exchanger, and from the template we will choose AEL. We will specify the design parameters, codes, design conditions we will enter for shell side, tube side. choose 0.75 megapascal 250C for shell side and 0.3 megapascal 120C for tube side design. We will set 8-inch nozzle, shell side, tube side, welding neck type. Change the accessory. Observe that you can also do single or stacked exchangers. We'll specify the gaskets. In the bundle, we will change the diameter, the value of the pitch, the straight tube length. We will specify a gauge. Maybe we will choose gauge 12 or 14. Let's stick with gauge 12. And let's change the pitch to 45 rotated square. Double segmental baffle we will choose with 25% cut for external central. We will keep 300 mm baffle spacing. The tube sheet layout, we will go for a mixed pass, having 4 tube side passes, and we will use we will design for 1000 tube numbers. We'll put an impingement baffle plate. So that designs the tube bundle layout. We'll apply materials, apply default data. Okay, so the preliminary design is complete. You can show the transparent wall, show all the tubes. You can see the pass partition plates very clearly, the tube side inlet outlet conditions, and the shell side inlet outlet nozzles. We'll go ahead and make some changes. Maybe we will want to see the tube passes, so click on that icon over there and it will show you the tube passes. There are 4 passes which are identified. So the fluid enters through 1 and eventually comes out through 4 after the completion of the 4th pass. We would like to change the dimensions of the baffle, impingement baffle. Likewise, we just double click on that and change the thickness, the gap between tubes, length, etc. Change length to 300 mm. Click OK. As you see, the changes are incorporated. It's very easy to work on the tube bundle. Now we will calculate, we'll complete the analysis. So we do have lots of errors, mainly due to tube sheet loading conditions, the tube to tube sheet joint overstress, the shell to channel joint stress, longitudinal membrane stress in the shell and tubes, they exceed. So this is a very common problem with double fixed tube sheets, and the reasons we will discuss very soon. So we will go ahead and include an expansion joint. There are different options. You can either design an expansion joint just by spring rate input data, or you can design full-fledged bellows type expansion joint. So you will put a spring rate there, 2000 decanewton per millimeter. We can right click and move to the center. And then we will recalculate. Now we see that there is absolutely no error. The design is completed and it's perfectly alright. And what it did is that it now includes the 20,000 Newton per millimeter spring factor in the calculations. Now we will generate the drawing. So drawings are generated in MicroStation. You can also create the drawings using AutoCAD. Shows the general assembly. Observe the level of details and also the tolerances on the dimensions. They're all automatically generated. The flange details, flange drawing. Observe that the tolerances are also mentioned. The items are called out automatically. This is the data table to the right, table of estimated weights, construction material, bill of material, etc. The tube sheet, stationary tube sheet drawings are pretty detailed and almost like fabrication level details are shown here. The nozzle location orientation table, nozzle projection, the baffle drawings, the channel, so now we will watch the design of a floating head exchanger, and in this video we would also review the tube sheet design features in details. So we will quickly design an AES floating head type design. Just like we did for the previous models, we'll enter the design conditions for the shell side, tube side, load conditions tab, operating conditions tab, welding neck nozzles, the gasket, the tube pitch, the gauge thicknesses, will be a double pass exchanger with 600 tubes. You can move the tie rods by right click and selecting move, and it completes the design of the floating head type exchanger. Okay, the calculations are done. And you see the design conditions, the supplementary design data, the geometry. These are the different tabs under the tube sheet properties window. The tube sheet material, the tube materials, the test flange material. So let's look at the design conditions tab. So you have the design conditions, all the design conditions are automatically generated in the program. So the software bases the calculation based on MAWP, but you can change those to design pressure values as well. For instance, from this drop down you can select 0.7 instead of MAWP. Okay, I can go ahead and change these from MAWP to design, and I can change them back to MAWP. So that's a very interesting and useful tool, the drop down menu. You can create additional design cases, as many as you want. So I'll create another design case with 0.5 megapascal shell side pressure, 290 C temperature, maybe 0.4 megapascal tube pressure, and I'll say this is an abnormal case, so you can select abnormal from the type. The channel, tube sheet temperatures, and then recalculate. So now if we review the report, as you see here, there is a corroded abnormal condition coming up with 0.4 megapascal tube side and 0.5 megapascal shell side. This is the abnormal special case, design case that we created, and that matches with our entry, the item number 6 under the design cases. Alright, so it's very easy to create additional design cases, as many as you want for the tube sheet design. This is the geometry section. You can change the machining exterior parameters. So I will change that to 15. As you see here to the right, it shows real time how much the machined dimension changes. So you can change to 7, keep it that way. The floating tube sheet also, you can change the parameters. You can see at the bottom left it is changing dynamically. So it gives you a very good idea real time of which exact parameter you're changing. Okay, I will keep it to 5 mm, maybe 12 mm on the shell side. Floating tube sheet design, shell support radius, I'll change to 10 mm. Tube extensions also you can change, and of course the tube sheet thickness, you can force the thickness that you want to consider. Although the software optimizes and calculates on its own, you can change the tube sheet thickness. So now let's go back to our AEL type exchanger that we did, and this shows you the different types of joints. The angle joint that is now shown, integral with barrel. You can have a butt joint with knuckle radius, you can have a butt joint with recessed knuckle radius and slope, and all these parameters you can change. Angle joint, so let's create a recessed knuckle radius and slope. So I will change the recessed face. So what is that? You can get help from the reference help, and it shows a small sketch explaining the parameters. I can change the recessed face to, let's say, 12 mm and change it back to maybe 10. Machining surface, I can change that dimension there as we did in the last AES type exchanger. Change it to 12, change it back to 10. Shell support radius we can change. Let's see what that means. So it shows you the shell support radius symbols, and you will know which parameter you're exactly changing. We'll put 20 mm, but that's too big, so we'll change that, make it smaller, maybe 5, 10, 30. It's very easy to change the dimensions on the fly, and it gives you very advanced control on the detailed tube sheet dimensioning. You can change the stress relief slope. So this slope is actually what is shown here. So 1/4 is input as 0.25. Alright, so this brings us to our last video in today's webinar, where we would review some of the additional features in the Supplementary Design tab of Tube Sheet Design window. So let's take a look at it. So we would review the Supplementary Design Data tab for the Tube Sheet Design for the AEL type exchanger that we created in one of the previous videos that we saw. So we will double click on the tube sheet and change the design code to AD2000. So this shows the various different sections. Starts from the design according to 6.7.2, 6.7.3. These are the various parameters that are required for AD Mark Letter 2000 code. So let's review what it is. So this is the design factor C, which is according to the AD2000 code. In section B5 table 1, the design factor C is specified for the various configurations of the tube sheet joint, the type of configuration that you're choosing for the tube sheet. So forged or pressed flat, flat plate welded, bolted, flat plate, and then flat plate with stress relief groove, the one that we just modified the geometry. So this factor C is actually a direct parameter which is used to calculate the thickness of the tube sheet for AD Mark Letter code. And then 6.7.2 is the circular fully perforated tube, and 6.7.3 is the partially or irregularly perforated flat tube plate for U-tubes. So these are actually the parameters which you enter there in the supplementary design data. There are some additional features for AD Margletter code. You can design the corroded only or for design new and corroded. Either way you can calculate. So let's consider a BEM type exchanger, and I will show you what is the meaning of the do not perform elastic plastic calculation. So let's calculate, and as you see here there are various errors that are reported in the final calculation, and this is coming because we checked the option for not to consider the elastic plastic calculation. Now we uncheck that and recalculate. So as you see here in ASME UHX, there's a special provision for calculating the tube sheet thickness based on the effect of plasticity at the tube sheet channel or shell joint. Now this is applicable only for certain configurations of tube sheet and also for certain criteria to be met. So if those criteria are met and you're designing tube sheets of certain configurations, then and then only you can apply that special elastic plastic calculation. So now we are going to consider that effect and we recalculate, and as you see the design passes this time and the thickness is also reduced to 38. You have various configuration options for tube to tube sheet joints: expanded only, equal fillet and groove welds, fillet weld only, expanded with groove weld, etc. You can specify expanded length, or you can say relative length based on the percentage of the tube sheet thickness. Number of grooves, 0, 1, etc. You can also check for the tube efficiency. So FR is nothing but the type of joint, based on the type of joint, the joint efficiency. So that brings us to the end of our webinar. I'd like to thank everyone for attending this presentation. Thank you.